All right, let's dive right in. We're going to break down this amazing method that lets us take pretty much any 3D object you can think of, from a massive building to your phone, and draw it perfectly on a flat 2D page. But first, just think about this for a second. How does an idea, for a car or a house, or even just the chair you're sitting in, actually become a real thing? It's not magic, that's for sure. It all comes down to speaking a very specific language. You see, before anyone can even think about building something, that idea has to be communicated flawlessly. We need a visual language that's so precise, an engineer in Tokyo and a builder in Toronto can look at the exact same drawing and know exactly what to do. It's basically the blueprint for our entire modern world. And this, right here, shows you the core problem we're trying to solve. Look at that 3D house. You can see its shape, its depth. Now look at the architect's plan below it. It's totally flat. So how in the world do you translate all that real-world 3D complexity into a 2D guide that someone can actually build from? Well, the answer is a system that's so solid, so universally understood, that it's the silent backbone of just about every physical thing we make today. It's not just one way of doing things, it's the global standard. And here it is, First Angle Orthographic Projection. I know, that name sounds super technical, right? And that first angle part? That's just one very common way of organizing the drawings. But trust me, the main idea behind it is actually incredibly simple, and once you get it, you'll start seeing it absolutely everywhere. Okay, so let's unfold this whole thing. How does this system actually let us look at a solid object from all these different angles, all on one single piece of paper? At its heart, it's really simple. Orthographic projection is just about looking at an object from a few very specific viewpoints, straight on from the front, directly from the top, and straight on from the side. By capturing these separate, flat views, we get a complete picture of the 3D object without any of the weird distortion you get with, say, a photograph. Now, this is the absolute best way to wrap your head around it. Just imagine your object is floating inside a clear glass box. You look at it from the front, and you trace its outline right onto the front pane of glass. Then you do the same from the top, and then from the side. Each tracing is a perfectly flat 2D view. So that very first tracing, the one where you're looking straight at the most important face of the object, that becomes our front view. Now, imagine you're hovering directly over that box, looking straight down. The tracing you make on that top piece of glass, that's your top view. You'll also hear it called the plan view. And finally, looking from the side gives us, you guessed it, the side view. And with just those three views, we have everything we need: the length, the width, and the height. All the essential info is there. Okay, but here's the really clever part. What happens next? We take that glass box and we metaphorically unfold it, laying it completely flat. And what we get is this: the three views, front, top, and side, all arranged perfectly on one single page in a standard layout. It's brilliant. So how does anyone looking at your drawing know which way you unfolded the box? They look for this little symbol. Think of it as the Rosetta Stone for the drawing. It instantly tells anyone, anywhere in the world, that this is a first angle projection and exactly how to read it. But just like any language, this one has its own grammar. It's not just about what views you draw, it's how you draw them. The types of lines you use and the scale you draw to, well, they carry a ton of essential meaning. You can think of line types like punctuation in a sentence. A thick, solid line, that's your full stop. It defines a clear, visible edge. But a dashed line, that's kind of like a whisper. It's showing you a hidden detail, an edge or feature that's definitely there, but you just can't see from that particular angle. And those faint construction lines are just your guides to make sure all the views line up perfectly. The other piece of this grammar is scale. I mean, you can't draw an entire skyscraper at its actual size on a piece of paper, right? So the scale tells you the ratio. A 1:2 scale means your drawing is half the size of the real thing. But for something super tiny, like the gears inside a watch, you might use a 2:1 scale to draw it twice as large just so you can see the details. All right, theory's great and all, but let's actually see how this works in practice. We're going to take a really basic shape and translate it into a proper orthographic drawing. We'll kick things off with the most fundamental 3D object there is, a simple cube. This is where you can really see how the three different views lock together to tell the complete story of an object. The process itself is just so logical. Check it out. Once you've got your front view drawn perfectly, you just project faint little construction lines straight up from its corners. Those lines give you the exact width for your top view, so you know everything's aligned. The same thing happens when you project lines across to draw the side view. It's almost foolproof. And this is what you get. Three simple squares, right? But arranged in this specific way, they communicate everything you need to know about that 3D cube with absolute precision. There is zero ambiguity. It's a perfect set of instructions that anyone who speaks this language can follow. So, why does all this matter? Why did we just spend all this time talking about views and lines and glass boxes? Well, let's zoom back out and connect this to the real world. And here we are, right back where we started. That architect's plan on the left, a classic top-down orthographic view, that's the instruction manual. It's only because of the clarity of this shared visual language that the amazing, complex 3D house next to it can be built, piece by piece, exactly how the designer pictured it. So, what's the big takeaway here? Orthographic projection is really just an elegant solution to what seems like an impossible problem. By combining a few simple views, front, top, and side, and using a clear grammar of lines and scale, it creates a totally unambiguous 2D plan for any 3D object you can imagine. It is, quite literally, the language we use to build our world. In the end, this isn't just some drafting technique. It's a whole new way of seeing and understanding the structure of everything around you. So I guess the question we'll leave you with is this. Now that you can read the language of creation, what could you build?